Hello, I'm Dr. Derek Fish. I've been running the University of Zululand Science Centre for the past 30 years, and this is the Essential Skills for Physical Science video series. We're going to be taking a careful look at the November 2024 Physical Science Paper 1, that's the physics paper. Now you can get this paper downloaded from the DBE website and the memo. So you might feel you don't need my input because you can just look up all the marking guidelines and correct answers on the memo. And of course, you're welcome to do that. But the memo shows many different alternatives for the markers, and that might confuse you. And secondly, the memo shows the correct answers, but not how to get them. And that's why I'm here, to explain to you very carefully, based on my more complete Essential Skills series, how to get to those answers. So Essential Skills is based on the fact that facts fade, experiments expire, but skills stick. And these skills will not just help you through your physics paper, but will help you in all your exams and indeed throughout life. If you have the booklet, on page 3 is a contents page, and this brief introduction to the exam is covered much more thoroughly in video 1.1 and from page 3 of the book. Now, if you think you don't need an introduction to the exam, just skip ahead using the timeline to the multiple choice section. If you feel you need a deeper introduction, then go to video 1.1, which does this very thoroughly. So, having been in contact with the examiners, we had the comments from the examiners that interpretations of graphs or graphing skills is a challenge for many learners. That's from the National Exam Report from 2024. In addition, that learners struggle to draw and label free body diagrams correctly, that learners still cannot work with scientific equations, again, a comment in the 2024 examiner's report, and that multiple choice questions are one of the weakest sections, and learners need to practice these apart from the exams. So this was the basis on which I devised Essential Skills during 2020, when we were all struck down with COVID. 4 essential skills. First of all, graphs, free body diagrams, scientific equations, and multiple choice and ratio questions. Now, you should know that for Physical Science Paper 1, there are 4 main sections, 2 large and 2 smaller. Mechanics is the biggest section, and again, video 1.1 from page 4 in the book covers this in much more detail. But remember, it's a 3-year curriculum. Essentially, it's from grade 10 all the way through to grade 12. So mechanics, wave, sound, and light is a small section and will just be examined in question 6 on the Doppler effect from grade 12. Electricity and magnetism is the other big section, and then a small section on matter and materials, which will just be the photoelectric effect, question 10. Please remember that grade 10 and 11 work is important in paper 1. From grade 11, you have Newton's laws, electrostatics, and electric circuits. Again, a comment from the examiner after the 24 exam. Lack of knowledge of topics taught in grade 10 and 11 could be seen in pupils' poor performance in question 8 on circuits. And I would say probably in question 7 on electrostatics as well. Now, you should know by now the structure of the exam, but again, just a quick recap if you don't. It's 150 marks in 3 hours. So 180 minutes for 150 marks. I would suggest you try to work at 1 minute per mark. It's a 15 mark question. Don't spend more than 15 minutes on it. That leaves you 10 minutes to read the paper at the beginning and 20 minutes to check and complete at the end. Don't get behind, because often questions 9 and 10 are easier, and it's a pity if you don't reach there. There are 4 levels of question. And the simplest one are the recall questions. But again, a comment from the examiner on the 24 exam. Recall questions are very poorly answered. Keywords and phrases were left out. Now, you should be getting 100% for recall because they are simply learning work. And in fact, I don't cover them in my videos because I can't help you to learn those things. That needs to be done by you. So the 4 sections, which have slightly different weightings, and you can see question 1, multiple choice, covers all the sections. There are 10 questions. Questions 2, 3, 4, and 5 cover mechanics. Question 6 is waves. Question 7, 8, and 9 on electricity, and question 10 on photoelectric effect. These are the performance per question in 2024. The average across the country for the entire exam was 49%, just below 50%. And you can see there were two particularly weak questions. Question 3, projectile motion. Question 10 on photoelectric effect. Question 6, the Doppler effect, was well answered, but otherwise the results in general were pretty average. And I'll be looking at all of these questions in great detail later in this video. You can also download the diagnostic reports from the DBE website, and they will give you details on how students did on individual questions. And you can see there's some that were as low as 13%. And of course, those are the ones that I will look at particularly in this video series. Now, these are the performance distribution curves for physical sciences over the last 5 years. You'll see they're all extremely similar. And with a pass mark of 30%, we see that 76% of pupils passed in 2024 and 24% of pupils failed. Now, that looks good, but if we put another line at 50%, which is really what I think we should all be aiming for at least, 71% of pupils got less than 50%. Only 29% got more than 50%. And if you want to do science at university, which I hope is your aim, you really should be aiming to be to the right of 50%. So that means that 47%, about half the students, got between 30 and 50%. Now, the aim of this video series is to help you get beyond that 50%, not just to pass, but actually to understand and to pass well. Recall questions in 2024 were 15 marks. There's usually 8 or 9 of those. There's usually about one every long question that asks you to define or state or define. So, for example, in 2.1, the question was define the term static friction, and an abbreviated answer was the force that opposes the motion of a stationary object parallel to a surface. So all those words are very important, and you can see that the average across the country for that short question was 34%, extremely low. So I really encourage you to spend some time, because again, the examiner's comment from 2024 that recall questions were extremely poorly answered. So again, this is just a brief introduction. If you want a longer introduction, you can watch video 1.1, but let's get on with the exam paper itself. So average for all the recall questions was 57%. Let's have a look at the multiple choice questions from the November 2024 paper 1, that is the physics paper. Now, in my essential skills series in video 7, starting from page 66 in my book, I look at a particular type of multiple choice questions, which we call ratio questions, and you can go to that video and they're covered extensively over there. Also, in the same video, I give 10 top tips to master multiple choice questions. They are repeated here, but I'm not going to go through them in detail. I refer you to video 7 and encourage you to go there. The one I just want to highlight again is number 5, find the relevant equation by knowing your data sheets. And remember the examiner's comment that multiple choice is one of the weakest sections, and learners really need to practice that. So the data sheets in my book, they're on page 38 and 39 and 40. And they are very nicely arranged for you, but it's good for you to know where the different sections are. Projectile motion is at the beginning, the 4 equations of motion. Question 2 on Newton's laws is the equations for force, but also question 4 on momentum. Question 5 on work, energy, and power, and followed by question 6, the Doppler effect, and question 10, the photoelectric effect. On the next page, on page 39, we have the electrostatics equations, question 7, the electric circuits and internal resistance equations, question 8, and then alternating current. Please notice also the constants sheet, and on the right here, I've just written the questions in which you might use these constants. You can see that G, the acceleration of gravity, comes up very often, but mostly the others come up once only. Now, on page 40, we encourage you to do a simple quiz by yourself or with a friend. Write down all the symbols from the data sheets and see if you can identify which quantity they refer to and which unit. This might not seem important, but you'll see how it comes up in answering our multiple choice questions. So how did students do in 2024? These are the national averages, average was 49% as a whole. And you can see, if I put in the 50% mark, you can see there were about 3 good questions, which had averages of 72%, 65, and 76%. And there were some which were quite bad, 1.4, which dealt with Newton's second law and work, energy, and power, and then 1.8, 1.9, and 1.10, which respectively dealt with long questions 8, 9, and 10, where the national averages were in the 30. So you can see a few good, a few bad, but we're going to look at all of these as I go through them. Now, every year the examiner puts out a diagnostic report. It's freely available on the Department of Basic Education website. I encourage you to get hold of it. There were suggestions for improvement. If you really want to look at them, you can pause the video here and the second page, or you can get the document off the website. But what I've done is I've summarized those suggestions. And in fact, I've put together the suggestions from 2023 and 2024. So the first suggestion was solve multiple choice questions by logical reasoning, not lengthy calculations. Use generalizations and predictions. These questions are worth 2 marks each, so you mustn't spend long on them. Sure, the data sheet is known really well, which I stress too. Practice multiple choice after each topic, not just in tests and exams, and start this in grade 8. Solve them by eliminating the distractors after reading all the options. You'll see how we do this later. Ensure you have a solid grasp of fundamental concepts and interconnections. Use apps like ZipGrade or Kahoot to help. Create a Google form. Include the use of ICT in teaching like PHET, Educite, or YouTube, and use different sources to get multiple choice questions. So some very good comments from the examiners who've just marked thousands of papers. So you can really pay attention to these. So the 2024 multiple choice questions, as usual, 10 questions worth 20 marks. So you should spend about 20 minutes, 2 minutes per question. And you can see 1.1 dealt with long question 2, Newton's laws of motion. 1.2 dealt with projectile motion and graphs of motion. 1.3 was a bit of a crossover question between 4 momentum and 5 work, energy, and power. 1.4, again, an integrated question between Newton's laws and work, energy, and power. And 1.5, another integrated question between projectile motion and momentum. Students often find these more difficult. 1.6 had to do with the Doppler effect from long question 6. 1.7, electrostatics. 1.8, electric current. 1.9, electrodynamics. And 1.10, the photoelectric effect. So that's a snapshot of all the questions. Now, of course, you can get all the questions from this exam paper. You can also get hold of the memo or the marking guidelines, but all of that will give you is this, the correct answers. It won't show you how to get the answers, which I am going to show you. So may I suggest that you pause or stop the video here for 20 minutes while you try to complete these 10 multiple choice questions for yourself from the 2024 exam paper. You will learn so much more if you try them yourself first. So please try that now. So assuming that you've tried them yourself, let's go through them now. Question 1.1 was quite well done. The national average was 72%. It says several forces are acting on a moving object. So as always, we go to our data sheet, and with force, we're looking at Newton's second law. Net or resultant force equals MA. And it says these forces are in equilibrium, which means the net force is 0. The net force is 0. The acceleration is 0. Acceleration is change in velocity over change in time. So that means the change in velocity is 0. The object is moving at a constant velocity, not too difficult. 1.2, not so well done, average 46%. And it gives a graph of acceleration versus time. Stone is thrown vertically downward from the top of a building, takes t seconds to strike the ground. Here's the acceleration time graph. Now notice the question is asking about the shaded area and what that represents. So this is looking at area under the graph for motion graphs. Now that height, of course, will be A, and that distance on the x-axis will be delta t. So that area is A times delta t. It's just length times breadth of a rectangle. Now, again, we know that the definition of acceleration is delta b by delta t. So just multiplying A dot delta t is equal to delta t. So the area is equal to the change in velocity. So the answer must be D, the change in velocity of the stone. Another way of looking at it from your equations of motion, V final is V initial plus A delta t. So V final minus V initial is A delta t. And of course, that is just the change in velocity of the stone. Note, not the velocity or the final velocity, but the change in velocity. 1.3, not too well done, average 41% nationally. This is a mixture of momentum and energy. You're told a ball going horizontally has momentum P and kinetic energy K. Ball collides with a wall and comes back horizontally with momentum half P. Now, again, our kinetic energy we get from our work energy and power equations. It's half mv squared. What you need to notice, there's your two equations, that if after the collision it only has half the momentum, because the mass of the ball remains constant, that means it only has half the velocity, of course, in the opposite direction, but that's not important. So the kinetic energy afterwards is half m, but now velocity is half velocity squared. And when you square that, you get a quarter of the original kinetic energy. So because the velocity is halved, kinetic energy, which depends on the square of velocity, is now 1/4. Question 1.4. Again, this is a mixture of Newton's laws and work energy and power. Got a force acting on a box. Now notice the force pulls up, but the box is still going down. In fact, you're told it accelerates down at constant acceleration. It's a rough incline, so there is friction. Now, this is quite tricky in terms of the wording of it. So you won't have time to do this thoroughly as I have, but just to make it clear, let's take our box. Let's do a quick free body diagram. Of course, it has weight, it has a normal force, it has the force F pulling it in the direction up the plane, and it has the force of kinetic friction, but the box is still accelerating down the plane. So obviously this gravitational force is strong enough to keep pulling it down, because we're told that there is a force down, an acceleration down the plane of ma. Now, we can get rid of our normal force because it's acting at 90 degrees the plane, and let's get rid of our weight and replace it with a component of the weight which is parallel to the plane. So that's the component of the gravitational force. Now we know that m times a, Newton's second law, is the force down the plane, the weight, minus the forces up the plane, which is F and the force of kinetic friction. But you know that that's greater than naught because it says it's a constant acceleration. If that's greater than naught, it means that the gravitational force is greater than the sum of the forces pulling against it, which is the force F and the frictional force. Now, if the gravitational force is larger and it's being accelerated down the plane, then the work done by the gravitational force is greater than the sum of the work done by the frictional force and the work done by F. So the wording is a bit tricky there, but I hope these equations and this help you around it. I understand that with 2 minutes, you don't have time to do all these drawings, but I'm just trying to make sure that you're clear how we get to the answer. 1.5, this is a mixture of projectile motion, long question 3, and also momentum. So a ball falls vertically, it bounces off the ground, it comes back to a lower height. Now already that tells us that the second velocity must have been less than the first. They're asking about the direction of the impulse on the ball and the magnitude of the velocity with which the ball leaves the ground. So once again, we go to our data sheets, page 38. There is the equation for impulse, F net delta t equals delta p, so it's the change in momentum. Now the ball was falling downwards. It has a large initial velocity when it strikes the ground, and it leaves the ground with a smaller velocity, v final, because we know that it doesn't rise as high. So we can put these together to say the direction of the impulse on the ball must be upward because it changes momentum from a downward momentum to an upward momentum. and the velocity must be less than v because it doesn't rise as high. Question 1.6, which is a Doppler question. It's asking about a redshift. Now, again, this is covered extensively in my video 6.6 and on page 55 in my book. But if you look at the diagram here, we know that when a star is moving away from the Earth, it's almost like the wavelengths of light are stretched out. So the wavelengths become bigger, but of course, frequency, which is the inverse of wavelength, becomes smaller. So we know that the frequency is decreased, and we know that a redshift is when something is moving away from the Earth. In fact, that's what Hubble discovered in the 1930s, that the universe is expanding. Everything is moving away from everything else. That's why all the spectra we see are redshifted. 1.7, again, to be honest, I'm surprised this was answered so well, 76% average, but I think this is quite a difficult question. So you've got two small charged spheres in a vertical cylinder. They remain stationary. Now, the bottom one is resting on the bottom of the cylinder, but let's consider the upper charged sphere. It has a mass m. If it's stationary, it means all the forces on it must be balanced. Now, of course, it has a weight pulling downwards, just F equals mg, and it has an upward force because of the electrostatic repulsion between the two spheres. And from Coulomb's law, that's just F equals kqq. They both have charge q over r squared. Now, as I said, if it is stationary, then those two forces must be equal and opposite. And so we can put mg equal to kqq over r squared. Bit of rearranging, we get that r squared is kq squared over mg. Now, the question says, which one of the following expressions, on the right I've put them, can be used to correctly calculate the distance r? Well, it must be that one, because if r squared is that, then r is equal to the square root. So it involved finding two equations and just putting them equal and manipulating it a bit. As I said, I'm pleasantly surprised the average was quite high. Question 1.8 was not well answered nationally. And again, it wasn't a difficult question, and it's a question about units. It says the kilowatt hour is a unit of, and you notice answer A, power. That's the one they're hoping you'll choose because you saw kilowatts. But a kilowatt hour is a combination of units. Now, again, when we look at our data sheets, we're looking at the power equations. The definition of power is its work divided by delta T. So power times delta T is equal to work. Now, this is power times time. And so therefore, we're looking at electrical energy. So when you take the unit of power, which is the watt or the kilowatt, you multiply it by the unit of time, which is hours or seconds. What you get is work, and the unit of that is joules for the electrical energy gained. Now, just for your interest, you didn't need to know this, but a kilowatt hour is obviously 1,000 watts or joules per second times 3,600 seconds. That's how many seconds are in an hour. When you multiply them out, you get 3.6 million joules of electrical energy. That's the unit that we use when we pay for our electricity in South Africa. Now, again, on page 40 in my booklet, I encourage you to do this exercise to make sure that you know what the symbols are on your data sheets, but more importantly, what quantities they represent and in what units they are measured. If you'd focused on the units, you'd have had no problems with question 1.8. Nearly finished. Question 1.9 on electrodynamics. Not well answered, and it wasn't a difficult question. Average was 39%. Now, we can immediately eliminate some distractors here, because in the statements, 2 of them are slip rings and 2 of them are commutators. Now, you should know from all you've studied that what we have here is a DC electric motor because we have a split ring commutator. So immediately, let's get rid of the 2 options, the distractors A and B, which talk about slip rings. You only have slip rings in an AC motor. And again, here you can see a battery. And you'd only have a battery or a DC power source with commutators. So the answer is C or D. To get the correct direction, we need to use our left-hand rule for electric motors. The field, of course, is directed north to south. The current is directed from the positive of the battery around. I've just used this side of the wire because it resembles my diagram more correctly. And that shows that we'll have an upward force on the right-hand side of the coil, which means that the commutator will rotate anti-clockwise. Finally, 1.10. Again, very badly answered, 33%, the worst question. Which of the following statements are true for the photoelectric effect? Now, this is difficult with the language. Photoelectric effect demonstrates three things. So either they're all right, or none of them are right, or one or two, and so on. So let's look at them slowly. Now, for this, we need to go back to our CAPS curriculum statement. If you look in grade 11, when you did optics, you did 2D and 3D wavefronts. We looked at diffraction, and you were told to understand that the diffraction of light demonstrates the wave nature of light. So the wave nature of light is demonstrated by things like diffraction, refraction, interference, reflection, and so on, but not by the photoelectric effect. So therefore, we're actually going to get rid of number one, because the photoelectric effect does not demonstrate that light has a wave nature. Let's check the other two statements. Again, when we go to the photoelectric effect in our CAPS document, you'll see there, if I enlarge it, it says, you must give the significance of the photoelectric effect, which establishes the quantum theory, and it illustrates the particle nature of light. So it establishes that light has a particle nature and that light energy is quantized, the quantum theory. So it's 2 and 3 only, and therefore the correct answer there is D. Now, once again, I've stressed this is the list of skills which are required from the CAPS curriculum document, and multiple choice questions are all about skills. There's no recall questions. There's no simple calculations. It's more conceptual skills. And if you focus on these skills, it will really help you with multiple choice. Again, a comment from the examiner. A severe lack of skills is evident. Mathematical, conceptual understanding, and integration of topics, free body diagrams, graphs, and equations. Again, these are the essential skills which I focus on in my videos. So that was the multiple choice. And we can now move on to the longer questions from the November 2024 paper. So let's look at question 2, which is the first of the long questions. Always on Newton's laws. In 2024, it was for 15 marks, and the average across the country was 54%. Not too bad, but not too great. Now, in my video 6.2 from page 42 in the book, I cover this section very thoroughly. So if this is a weak point for you, I encourage you to go and look at that. But for now, let's look at just 2024. Now, you can see a trend. I've shown you some snapshots of previous exams. And usually there's two types. Either there's an inclined plane like 2019, or like 2018 and 2020, an object on a table and hanging masses pulling via a pulley. You can see also 2021 was an inclined plane, 23 an inclined plane, 24 was again a pulley over the table, and in this case, reading data off a graph. Now, in my video, I introduced the acronym FEAR, which stood for Free Body Diagram, Equation, Application, and Recall. And these are all the different parts of this question. Now, in November 2019, it was a 17-mark question, and you can see that most of the marks always go to the equation. And if you want to be able to do these, free body diagrams are covered extensively in my video 5. You can look at that. Equations, video 6.1 deals with equations generally and a general method called progress for solving them. 6.2 deals specifically with Newton's second law equations. The application really just requires understanding. The recall question just needs to be learnt. November 21, that was the mark breakdown. Equation was about half of it. November 23, that was the pupil's performance. And you can see again, the application was very weak, and it shows a low level of understanding there. Now, it's important with every one of these long questions to know which equations and variables to use. So on page 38 in my book are the data sheets. Make sure you get to know them. And the second section on force really deals with Newton's laws, which are the equations surrounded with a red box. The ones with the blue box are friction, and we will need both of those for this question from 2024. And the ones with green are gravitation, which didn't come up in this exam. So here's the question. It was a 15-mark question. Crate of mass 8.5 kilograms is lying stationary on a rough horizontal table. I've highlighted rough to remind us that that means there'll be friction. It's connected to a mass hanger by means of a light inextensible string. Inextensible just means can't be stretched, passing over a frictionless pulley as shown in the diagram. Mass pieces are added and the acceleration of the crate is measured. Experiment is repeated several times and this graph is drawn. Now, define the term static friction is the recall question. I'm going to leave that for you to cover. We will move straight on to 2.2, which is the free body diagram. Just 2 marks, as it just asks for all the horizontal forces on the crate. So you can indicate the crate. You don't need to draw the whole crate. There's a force of static friction to the left, or as opposing motion, force of tension in the string to the right. And that's all you need for your 2 mark. You don't have to color it like I have. And you would not be penalized if you added the vertical forces, but you also wouldn't get any marks. So please don't waste your time on that. Just make sure that your arrows do touch the object and that there are arrows, not just lines, and that they are labeled. Moving on to the equation. 4 plus 5 is 9 marks out of 15. That's 60% of the question, so very important. Calculate the coefficient of static friction and the magnitude of the acceleration represented by y. Now, what we need to get off the graph is a realization that static friction is what prevents the box from moving. And so static friction can be calculated from the maximum friction to be overcome before motion starts. Now we can see that motion started there because up till there, the acceleration is 0. So motion starts when the hanging mass reached 4.2. That was enough of a downward force and a tension force to start that box moving. And so we can use that mass to calculate the coefficient of static friction. So the maximum force of static friction at that point was equal to the tension in the string, which was provided by the weight, the hanging weight. So static friction was the coefficient of friction times the normal force, and the hanging weight was the hanging mass times g. Now I've used small m for the hanging mass and big M for the mass of the crate. So putting in the figures, we can cancel the g's, and we can say the coefficient of static friction times 8.5, the mass of the crate, is equal to 4.2. We read that off the graph. That was the mass, the hanging mass at the time that motion started. And so we can calculate that the coefficient of static friction is 0.49. Remember, it has no units, it's a ratio, and it's simply a coefficient. Now, we always expect that static friction will be higher than kinetic friction. And in fact, in the next question, we see that the coefficient of kinetic friction was 0.4, as we expect. Now, we want to calculate the acceleration represented by y when the hanging mass was 7.4. Again, we get those figures off the graph. So let's look at the forces involved. For the crate, the tension force to the right minus the kinetic friction to the left will give us the acceleration times the mass of the crate. So that's Newton's second law of motion. The net force is equal to the mass times acceleration. For the hanger, the tension force in the string pulling upwards, the weight pulling downwards, and that will give us the acceleration of the hanging mass times A. Now, putting these together, we don't know what the tension force is, but we don't actually have to calculate it directly. So that is Newton's second law for the crate. That is Newton's second law for the hanging mass, but of course the tension forces are the same. So by adding those two equations, we can eliminate tension, and then mg minus fk is equal to the sum of the masses times the acceleration. Now, of course, let's focus. It's the acceleration that we want to calculate and just the magnitude. And we also know that the force of kinetic friction, which we need there, will be the coefficient, which we were given, times the mass of the crate, 8.5 times g. So we could put all those figures in. Small m was 7.4, we read off the graph, times g, 9.8. force of kinetic friction was the coefficient 0.4 times 8.5, the mass of the crate, times g 9.8, and that's equal to the sum of the two masses times the acceleration. And then we can calculate that the acceleration, which is y on the graph, is 2.47 meters per second squared. Just the magnitude, so we don't need to give a direction, but of course the acceleration of the crate would have been to the right. Now, the application question. If we add a 5 kilogram block and the experiment is repeated, how will this affect the maximum static frictional force now experienced by the crate? We just need to choose a word and give a reason. Now, of course, it will increase because now that the crate is heavier by 5 kilograms, the normal force increases and static friction depends on that normal force. So that was question 2, and that was worth 15 marks there. So question 3 from November 2024 on vertical projectile motion was 16 marks, was very poorly answered, national average being just 35%. So I'd suggest you have a careful look at this question. Now, this question is covered extensively in my video 6.3 from page 48 of the book, but graphs of motion are covered very carefully in video 2 with lots of examples given. Now, here's a snapshot, and you can already see 2019 and 2020 had graphs. 2021, no graphs, but 2023 graphs again, and 2024 graphs again. So I really encourage you to have a look at both these videos as a background to answering question 3. But let's get on to the November 2024 question. As always, we need to go to our equations, and right at the top of our data sheet on page 38 in my book, the equations on projectile motion. Now, there are 5 variables involved here in blue. And as I said to you in the other videos, it's actually easier to choose an equation not by what variables are in it, but by what variables are not in it. So in my video 6.3, I spent some time explaining this table method to choose which of the 4 equations of motion to use based on what variable you have no information of. But that'll become clear when we look at this question. So here's the question from November 24, 60 marks. Ball A is thrown vertically upwards, and so on and so on. And they want you initially to calculate from the graph the time t, the position z, and the position y. Now, I'd strongly suggest that you take the graph and you take the information that was given and add it to the graph. So that is the height of the building. I would strongly suggest that you choose upward motion as positive. You don't have to. You can choose down, but I really think it's much easier, and that's the way I will be giving the answer. The memo gives for both upwards and downwards as positive. A was thrown upwards at 12 meters per second. B was thrown downwards at minus 5.4. And we remember that 2 seconds after A was thrown, B was thrown, and that our acceleration of gravity is minus 9.8 meters per second squared. It's minus because we've chosen upward motion as positive. So now all the information we need is on the graph, and I think that's easier than reading it all out of the question. So calculate the value of t. Now, I strongly suggest that you use this table method, at least initially, to choose the correct equation. There are 4 equations of motion. It's not always clear which one to choose. So let's take the information we have for both balls A and B, and let's put them in the table. Now, the y value of where they started, we don't know. We just call that z for now. We'll have to calculate in the next question, but it is the same for both. Same starting point. Initial velocity for A was 12, for B was minus 5.4. Final velocity we don't know for either balls, and they are not the same. Same acceleration of minus 9.8 due to gravity. And that value t, the time of flight for A was t, but for B it was t minus 2 because B was only thrown 2 seconds later. Now we're going to need to put together 2 simultaneous equations. And which equation do we use? Well, we know nothing about final velocity, and equation 3 does not contain final velocity. So that's the equation which we're going to choose. It seems like we have two other unknowns, but we are going to come up with simultaneous equations. And we can solve for two unknowns from two equations. So there's the equation. There's the data for ball A. There's the data for ball B. Remember, focus, we're trying to calculate the value of t. And we're going to use the fact that z, or that height, will be the same for both of the balls. So delta YA is VI delta t plus half A delta t squared from our equation. And we can fill in the values that we have from there. Delta YB, I've put A in green and B in blue. We can fill in the values, but remember it's t minus 2, not just t. So it is a little bit more complicated. Now we're going to work with the fact that delta YA is equal to delta YB and is equal to Z, the height of the building. So putting those two equations together, we get this really quite complicated equation, which is rather tedious, but it needs to be worked out and solved. And that will give you t is equal to 4 seconds. Remember, that's the whole time from naught. So B's time of flight was 4 minus 2, which is 2. A's time of flight was 4 seconds. Now, that was 5 marks. And actually, that's a lot of work for 5 marks. You get 1 mark for choosing a correct equation, 2 marks for filling in correctly for A, another mark for substituting correctly for B, another mark for noting that delta YA is equal to delta YB, and 1 mark for the answer. You don't even get marks for this long equation here and for sorting it out, only if you get to the answers. That was quite tricky and really quite few marks for that, but I hope this makes it clear how we chose our method. 312, calculate the value of Z. Now again, filling in the values, we now know what t is, so we've put that into our table. We still don't know the final velocity, so we're still going to choose the same equation because we don't know the final velocity. And in the last question, we set up that equation for A, and we set up that equation for B. Now, of course, Z is the same for A and B, so you can use either A or B to calculate it. Looking at those, don't you think A looks a whole lot easier? So you can do it either way, you'll get the same answer, but I'd strongly suggest you proceed with the figures for A. So Z, or delta YA, is equal to 12 times 4. We now know that t is equal to 4, plus half minus 9.8 for g times 4 squared, and we get that z is equal to 30.4 meters. Now, if you use delta YB, you would have got exactly the same answer and would have got full marks, but this is only 3 marks, 1 for the equation, 1 for the substitution, and 1 for the answer. So I suggest this is the quickest way to get there. And then finally, calculate the value of y. So y is the maximum height that A reached. So we only need to focus on ball A now because B had nothing to do with that y. What we're going to do, we know what z is. So we're going to calculate delta y, the difference between z and y on the graph, and then just add that to z. Now we're going to choose a different equation of motion because we don't know the time taken for A to go from z up to the highest point y. We don't know the time. So we're going to choose an equation which actually leaves that particular time out. And we're going to use v final squared equals v initial squared plus 2a delta y. Now, we do know what the final velocity is. It will be 0 because that was the highest point in the rise. So those are the figures that we've got. And we can simply substitute in 0 for final velocity, 12 for initial velocity, minus 9.8 for g, and do our calculation, and we get delta y equals 7.35 meters. Apologies, I've left out a 2 there, but the answer is correct. Now, the total distance y is equal to z plus delta y, and that's equal to 30.4. We calculated in the previous question, plus 7.35. And that's equal to 37.75 meters. Again, marks, 4 marks, 1 for the equation, 1 for the substitution, 1 for adding together the two distances, and 1 for the final answer. Okay, and then question 3.2. On the same set of axes, sketch velocity time graphs for ball A and B while they're in free fall, label them, and indicate the initial velocity of each ball. Well, that's easy. We've already indicated on that graph the time at which each ball was thrown, well, that was 0 for A and 2 seconds for B. The time at which the ball struck the ground, we calculated previously to be 4 seconds. So those are the things which must be put on the graph. So that is what the graph is going to look like. Now, if you find it difficult to relate a parabolic position time graph to a straight line negative gradient velocity graph, I'd recommend you look at video 2, and in page 13 in my book, there was an exercise, and you'll see that where the position time graph is a parabola, the velocity time graph is a straight line with negative gradient. And so I encourage, if this confuses you, go and look at that. Now, how is this graph marked? Well, the correct initial velocities, 12 and minus 5.4, must be there in the correct shape, both straight line graphs with negative slopes. Secondly, correct initial times of 0 and 2, and B must start after the intercept of A. Okay, because B was thrown after A reached its highest point. Thirdly, both graphs must end at 4 seconds, or if you just put T, that's acceptable. And finally, the graphs must be parallel to each other, but they've both got a gradient of minus 9.8 for G, and B must be to the right of A. Now, we know that A would land with a higher negative velocity than B because of how it started, so therefore B must be to the right of A to end up with a lower velocity than A. Okay, so that was question 3. Again, the average was 35%. People did very badly in that. So I encourage you to look carefully at that and come to the right answers for that. Question 4, the momentum question. This was worth 12 marks. The national average 54%, not too bad. And this is covered in video 6.4. If you want to look at more momentum questions and the theory of momentum from page 49 in my book. So momentum questions come in various shapes and sizes. And here are the ones from 2018, 2019, and 2020, just to give you a snapshot. In 2021, we had again a collision between two objects. 2023, a bullet colliding with and embedding itself in a block. And this year, 2024, is actually a crossover between momentum and energy, because we have two objects stationary, so initial momentum 0. When a spring is released, it pushes B up a slope, and we're going to use that slope and kinetic and potential energy to calculate what the velocity of B was, and then work backwards towards the velocity of A. So here is the question. Two objects, 1.5 and 2 kilograms. As I said, initial momentum is 0, so final momentum must be 0, which means that the momentum of A and B must be equal and opposite after they start moving. And B is pushed up a frictionless slope to a height of 1.5 meters. Now, momentum, the equations are on page 38, the first page of the data sheets, particularly P equals mv, the definition of momentum, and your impulse and change in momentum equations will be needed here. You're also going to need the work energy and power equations lower down that page, particularly kinetic energy and potential energy. So the recall question, write down the principle of conservation of mechanical energy. I'll leave for you to learn. Let's look at 4.2. Calculate the speed of trolley B at the bottom of the inclined plane. Now, we're going to work on the fact that the total mechanical energy of B at the top is equal to the total mechanical energy at the bottom. That's conservation of energy. So basically, total mechanical energy is potential and kinetic. And at the top, it just had potential energy because it wasn't moving. At the bottom, it just had kinetic energy because it had no height. So all we need to do, we can actually just ignore the masses. But if we substitute there, 2 kilograms times G times 1.5, which was the height reached, equals half times 2 the mass times V squared. Simple calculation gives you that the velocity of B at the bottom is 5.42 meters per second. You don't need to give a direction because the question asks for the speed, not the velocity. Now, for the t seconds the spring takes to return to its natural length, calculate the change in momentum of trolley B. Now, we know from 4.2 that the velocity of B at the bottom of the slope was 5.42 meters per second. So change in momentum is just final momentum minus initial momentum, which is the mass 2 kilograms times the final velocity 5.42. Initial velocity there was 0. And so a simple calculation gives you that the change in momentum for trolley B was 10.84 kilogram meters per second to the right. Now, momentum is a vector, so it is important to give the direction there. 4.3.2 is only 1 mark. Write down the change in momentum in trolley A. And because it's only 1 mark, it should tell you that we can just simply say 10.84 kilogram meters per second to the left. Because initial total momentum was 0, final total momentum must also be 0. So those must be equal and opposite, 1 to the right and 1 to the left. And we would make one of those directions negative. Calculate the speed of trolley A after t seconds. T was just the time of acceleration by the spring. So again, we know that the change in momentum of A was 10.84 kilogram meters per second to the left. So the change in momentum, which is mvf minus mvi, we know is 10.84. It's negative as it was to the left. So 1.5, the mass of A, times the final velocity minus 0. That was the initial velocity in the left-hand picture. Simple calculation, that final velocity is equal to 7.23 meters per second. So that one was not too difficult and should have been a fairly easy way to get 12 marks there. Right, question 5 on work, energy, and power. Again, a shorter question for 12 marks in 2024. National average was 54%. This is covered extensively in my video 6.5 and from page 52 in the book. So if you struggle with this one, I encourage you to look through that. Now, for quite a while, the questions were all around potential and kinetic energy being conserved as an object went up or down a slope. But we can see actually in November 2021, the same sort of thing, but November 23, horizontal movement only and a graph, which you had to read off. And November 24, again, horizontal movement only. So only looking at the work equation and at kinetic energy, no potential energy involved. So here's the question. Constant force is applied at an angle of 30 degrees horizontal. A crate of mass 6 kilograms initially at rest. Constant frictional force of 10 newtons acts on the crate as it moves along. Distance is 1.5 meters. The speed of the crate at point B is 2 meters per second. Now, again, I encourage you to put all these things on the diagram so you don't have to read through the introduction every time. Kinetic friction, always opposing motion to the left of 10 newtons. Final velocity at B would be 2 meters per second to the right. And everything else is there on it. Now, 5.2 asks you to draw a labeled free body diagram showing all the forces acting on the crate as it moves. And this is 4 marks. So they're going to be 4 forces. So actually more complicated than the free body diagram question in question 2. So once again, start with your object. The easiest force is always the weight due to gravity. There's a normal force equal and opposite to it because it's flat, it's not an inclined plane. We have the force of kinetic friction to the left, and we have the force upwards to the right. So those are different labels which you can use, but again, I encourage you just to use the simplest labels possible. And here are how the marks are awarded. Label and arrow are important. They must touch the object, and the length of arrows is not important, because you're not expected to draw it to scale. Now, that will be important also in the next part of the question. In terms of equations, on page 38, we have the work, energy, and power equations. We're going to need the work equation, and we're going to need the kinetic energy equation here. And also just acknowledge that the net work done is the change in kinetic energy. Now, please note it says using energy principles only, calculate the magnitude of force F. So do not use equations of motion. It can be done by that. Remember, you have a frictional force of 10 newtons to the left. You have a final velocity of 2 meters per second. And obviously, the force that produces that acceleration is the horizontal component of F. which I've put there in red, which is F cos theta. So the net work done is the change in kinetic energy, and the net work done is the net force, which is the horizontal force F cos theta minus force of kinetic friction, so that's the horizontal force, times delta x, which will be the 1.5 meters times cos theta, equals the final kinetic energy minus the initial kinetic energy. Now, everything is horizontal, so that's just the cos of naught, which is just 1. The object is 6 kilograms. We fill in the mass over there. Final velocity of 2 meters per second. Initial velocity was 0. And remember, we're trying to calculate the magnitude of F. We know the kinetic frictional force is 10. That was given. So we just need to calculate there. So we have everything we need there, except for F. We can calculate cos of theta, and that will give us F is 20.78 newtons. Question said calculate the magnitude, so you don't need to give the direction. So 4 marks for those 4 steps. Then it says a 2 kilogram object is placed in the crate. What effect will this have on the work done by the same force when the crate is again moved from point A to point B? Well, the work done remains the same. You don't have to give a reason. That is worth 2 marks. But just if you're interested, remember the work done is F delta x cos theta. It doesn't depend on the mass. And so that's why the amount of work done would remain the same. But that one not too difficult. That was question 5 on work, energy, and power. Right, question 6 on the Doppler effect. A short question worth 12 marks, but was well answered, and the national average 74%. So this didn't cause too many problems. Again, here's a snapshot of 3 previous Doppler effect questions. And you can see in particular graphs in 2019 and 2020. 2021, again, just a similar ambulance siren passing an observer. 2023, very similar again, but 2024, again, graphs. I want you to look at the snapshot because there's 3 questions. Each one have graphs. The graphs all have a horizontal time axis, but they are very different graphs. And again, I'd encourage you to look at my video 6.6 from page 55 in my booklet, where I do the other 2 graphs, November 2019 and November 2020. November 2019 in particular caused a lot of problems and people did very badly. Looking at November 2020, this graph is the frequency observed by a detector next to the road, that's the listener, and you can see the frequency actually drops. We've got that step graph. And so at T1 is when the source making the sound actually passed the listener by the road. November 2019, there's 2 graphs. The lower one is for the detector next to the road, and the upper one is for the detector in the car. And again, these are air pressure versus time graphs, so very different. And then in this exam, November 2024, again, 2 graphs. The lower one is for the source, the detector in the car, the police car, and the higher one, the detector next to the road or the listener. And this is a wavelength graph. Now, again, none of these 2 graphs, 2024 and 2019, record the change like this one does. This is just a continuous reading. And in this case, we're going to see that it's after the car has passed the observer, the listener, and is moving away from it. So let's get into it. Here's the question. A stationary listener standing by the roadside records the wavelength of a sound emitted by the siren of a police car, and it's traveling at a constant velocity. In the wavelength time graph, which is not drawn to scale, lambda L is the wavelength of the sound recorded by the listener. That's the top graph. And lambda S is the wavelength of the sound emitted by the siren. That is the lower graph in this case. You're given that the speed of sound in air is 343 meters per second. Now, again, I spent a lot more time on this in my video 6.6, but you can see with this great animation, after the source with a constant frequency has passed the listener, he observes a lower frequency. We'll see it one more time. As he approaches, the frequency is higher, 820, although the source is 800. And as the source moves away from the listener, he observes a lower frequency. Lower frequency will actually be a longer wavelength. And so we can say that the source or the car is moving away from the listener. And the reason is that the wavelength of sound is longer than the wavelength of sound emitted by the source. You could also say that the frequency is higher, but as this is a wavelength graph, that seems to be more direct. Now, very simple calculations. Calculate the frequency of sound emitted by the siren for 3 marks. And it's the sound emitted by the siren. So we focus on this figure, 0.38. That was the wavelength of the sound emitted by the source. So we use our wave equation, V equals frequency times wavelength, and it's the frequency of the source in this case. So 343, the speed of sound was given. 0.38 is the wavelength we get from the graph, and the frequency of the source is 902.63 hertz. Now that's 3 marks, and you finish the question. But while we're there, there's your 3 marks which are given. While we're there, let's also calculate the frequency observed by the listener. And we do exactly the same calculation again, but for the listener, we use 0.4 as the wavelength, and we work out that the frequency observed by the listener is 857.5. Now, as we expect, the listener observes a lower frequency than the source because the car is moving away, and those waves are getting stretched, which means longer wavelength and lower frequency. Just again, what's in red is not required for 6.3.1, but we will use it for 6.3.2. Now, on page 38 in my video 6.6, I spend a lot of time talking about how to choose the correct equation, because this Doppler effect equation comes in 4 different forms. And we must identify that in this question, the police car is moving away from a stationary listener. So we need this particular one here, this 3rd equation, because the source is moving away from a stationary listener. So here's your listener by the side of the road. The velocity of the listener is 0. And that's why that velocity of the listener comes out of the equation. Police car is moving away. It's making a sound, but those sound waves are being stretched. So longer wavelength, shorter frequency. And that's the velocity of the police car, which is what we're going to be asked to calculate. And we notice that the frequency observed by the listener is going to be less than the frequency produced by the source. Frequency observed by the listener, we calculated in the last question to be 857.5 hertz. And the frequency of the source, we also calculated to be 902.63. Again, it's greater as we expected. So calculate the magnitude of the velocity of the car, which is the source. Really, we just take that Doppler equation. We're given the fact that the speed of sound is 343 meters per second. That's V. We've calculated previously that the frequency observed by the listener was 857.5. Frequency produced by the source was 902.63. So it's simply a matter of substituting them into that equation there, and then just solving for Vs, which is the velocity of the source of the car, which will give us Vs is equal to 18.05 meters per second. 1 mark for choosing the correct form of the equation, 1 mark for each of those frequencies and substituting correctly into the equation, and 1 mark for the final answer. So sorry, the substitution carried 3 marks, 1 for each frequency and 1 for the speed of sound in air. So really not too difficult in this particular question. Question 7 on electrostatics, based mostly on your grade 11 work. 14 marks and national average 52%. So not terrible, but not the best. This is covered extensively in video 6.7 from page 58 in my book. So if you want more exam questions and more on the theory and the equations and quantities, make sure to look at that video. So there's again a snapshot of 3 exam questions. And even when I add the more recent exam questions, you can see that we nearly always have a couple of charges separated by some distance, and then we have to calculate either forces or electric fields between the charges. So very similar questions, just obviously slightly different initial conditions. So here's question 7 from November 24. It says P is a plus 2 nanocoulomb point charge, X is a 0.6 centimeters away. calculate the magnitude of the electric field at x. Now, just a very simple equation. The electric field strength at a distance r from a point charge q is just kq over r squared. K is Coulomb's constant, 9 times 10 to the 9. The charge, we're told, is 2 nanocoulombs. You need to know that nano means 10 to the minus 9. And divided by the distance. Make sure that 6 centimeters is expressed in meters in SI units before you square it. Simple calculation gives you 5,000 newtons per coulomb. Now, it might look to you like that's not related to the rest of the question, but actually it is. So let's not forget about this calculation. Point charge S with a charge of minus 2 nanocoulombs is placed 4 centimeters to the right of P. Draw the resultant electric field pattern. So you've got two equal and opposite charges, and the field pattern looks like this, and it's marked. The shape must be correct. The correct shape of the electric field lines, and on the outside of the charges, not going into the charges. No field lines must cross each other. They must touch the charges but not go into them. If you just put in two like charges, you get 0. And if you only put one charge, you get 0. So it's 3 marks. And you can see how the 3 marks are allocated. Obviously, the direction is always from positive to negative, the direction of the force that would be experienced by a unit positive charge. Now, if you need to know more about electric field diagrams, please go back to my video 6.7 from page 58 in the book. I use this fantastic simulation from PHET called Charges and Fields. In fact, in that section, I use 4 different simulations, and it really is very instructive. So I encourage you to go there. And you can see I've set up the field here, and you can see the shape. And this field actually changes dynamically as you move the charges around. So have a look at that. It'll help you understand electric field patterns much better. 7.3 says a third charge T placed 2 centimeters to the right of S, experiences a net electrostatic force of 2.5 times 10 to the minus 4 newtons to the left. Again, I like to add things to the diagrams that all the information is now in the diagram. State Coulomb's law in words. Well, that's a recall question which you can learn. What is the polarity of charge T? Well, the fact that it experiences a force to the left says it must be positive. Although it experiences forces from both the charges are both 2 nanocoulombs, and the closer one is negative. The fact that T experiences a force to the left will tell you that it's positive, and then calculate the magnitude of charge T. You can see I'm doing this in slightly different order, but looking at the calculations together now. So calculate the magnitude of charge T. Our data sheets, page 39, the second page, you have all your electrostatics equations. That's Coulomb's law, which you may or may not need. And we've already used E equals kq over r squared, and also the definition of the electric field force per unit charge. Now, in doing this particular one, there are 2 ways of doing it. You can either do it using Coulomb's law, or you can do it using electric fields. And I want to suggest to you that the electric field way is much better because it is simpler. So this is the way to do it with Coulomb's law. There's a net force to the left. There's a force on T because of S, which will be to the left. There's a force on T because of P, which will be to the right. The resultant of those 2 is a net force. Now, this is the calculation directly from the memo, and you're welcome to do it this way, but I want to suggest this is a whole lot of calculating and a great opportunity to make mistakes. So I would actually recommend not using Coulomb's law and forces, but rather using electric fields. Okay. So you could also note that there's an electric field at T because of charge S, which will be stronger because S is closer. There's an electric field at T because of charge P. Now, we actually calculated that in 7.1, because 4 plus 2 is 6 centimeters. So in 7.1, we calculated the electric field at T due to P is 5,000 newtons per coulomb. Now, let's take left as positive, seeing as most of our arrows are going left. You can do it either way. And let's calculate the electric field due to charge S. So that's the same as we calculated in 7.1. Coulomb's constant times the charge times the distance, 2 centimeters, expressed in meters squared, which gives you 45,000 newtons per coulomb. So we can fill that in, and we now have everything we need. The net electric field is ES minus EP, taking left as positive. 45,000 minus 5,000 is 40,000 newtons per coulomb. Using our definition of the electric field, F equals EQ, we know the force is 2.5 times 10 to the minus 4 newtons. We were giving that equals E, the net electric field, times the charge, and that gives us a charge of 6.25 times 10 to the minus 9 coulombs. I'd suggest this is a much easier way to answer this particular question. Right, let's look at question 8 on electric circuits and internal resistance. This was worth 21 marks. It was a big question, and the national average was just 44%, so not particularly well answered. It was quite tricky in November 2024, and they brought in something new, which is worth paying attention to. There are 2 of my videos which cover electric circuits. Video 4.1 covers electric circuits and Ohm's law, series and parallel. 4.2 covers internal resistance. All the experiments are done and many exam questions are looked at, particularly 3 below. And you'll notice in 2018 and 2019, there were graphs, very different graphs. 2020 was a basic circuit analysis. 2021, again, a circuit, 23 and 24. So we haven't seen graphs for a long time in this question. What was very different in November 2024 is normally bulbs and resistors give their resistance is given in ohms. In this case, we had 2 lamps, and they were rated in terms of their power and their voltage. So quite different, and that confused a lot of people. Let's see how to handle this. So here's the question. L1 and L2 are 2 light bulbs that have the following ratings. So the power and the voltage is given. Bulbs are connected as shown in the circuit diagram. Please notice you've got 2 parallel branches and a series branch. The examiner commented that pupils don't seem to know the difference. Battery has an internal resistance of 0.6 ohms, and R1 and R2 are resistors. R2, we're told, is 4 ohms. R1, we're going to calculate. You're asked to define the term power. That's your recall question I will leave for you to do. I like to fill in all the information on the circuit diagram. So we could use the power equation B squared over R to calculate the resistances for each of the bulbs. And as well as the power ratings, we could also add the resistances. Now, I would suggest actually that we don't go this route, but I'm just showing you that that power rating actually defines the resistance of each bulb. But it's actually better to work with the power, and you'll see why in a moment. Okay, of course, we need to go to our data sheets, page 39, electric circuits. Don't confuse it with the electrostatics section, but we're certainly going to use Ohm's law, R equals V over I. We're going to use the fact that resistors in series should be added. We won't need the parallel one in this case. We'll certainly need the EMF equation, but in a slightly different form. And we're going to need our electrical power equations. So 8.2, 4 calculations, which together count 14 marks, which is quite a lot, quite a large part of this. If both bulbs operate as rated, calculate 4 different things. Now, the fact that they operate as rated means that you can assume that this bulb will dissipate power at 48 watts and will have 32 volts through it, and this bulb will have 20 volts through it. So to get the reading on ammeter A2, which is here, we can simply use the power and voltage to calculate the current according to that equation. So that's going to be very easy. To get the reading on ammeter A1 in the external circuit, we'll do the same for lamp L1, and then we will simply add the currents in the 2 parallel branches to get A1. To get the resistance of R1, we're going to need to calculate the voltage across R1, and then knowing the current, which we've already calculated in the previous question, we can calculate the resistance. The EMF of the battery, we will use the familiar equation, but in the form V external, which of course is I times big R, plus I times small r. So that's just to give us a snapshot, so we have a strategy for going ahead. So let's start with 8.2.1, the reading on ammeter A2. Let's focus our attention. That's what we're looking at. Now, for light bulb L2 over there, P equals VI, and we know the power is 48 watts, the voltage is 32 volts, so it's very simple to solve and get I equals 1.5 amps. So let's add that to our circuit diagram. So the current through that parallel branch is 1.5 amps. 822, the reading on ammeter A1. We're going to do the same as we did before, but now for L1, same equation, P equals VI, pull in 36 watts and 20 volts, and we get a current of 1.8 amps. And we can fill that in on our diagram. Now, you should know that for a parallel circuit, we add together the currents to get the total current flowing through the external ammeter A1, which is 3.3 amps. And let's also add that to our circuit diagram. 8.2.3, resistance of R1. Well, we need to know the voltage across R1. Although this 32 volts is for the whole parallel circuit because there's no voltage drop across an ammeter, here you've got two resistors. So that 20 volts does not apply to the whole circuit. In fact, we should know that that whole parallel branch will also have a voltage across it of 32 volts. So voltage across R1 plus the voltage across L1 are equal to the parallel voltage, which is 32. And we know that's 20 volts. So very easily we calculate that the voltage across R1 is 12 volts. Now we can simply use Ohm's law, V equals IR, and we can say 12 volts we calculated. 1.8 amps is the current we calculated in the previous question, gives you a resistance for R1 of 6.67 ohms. And again, we can add that to our circuit diagram. Finally, the EMF of the battery. So we're focusing on the battery with the internal resistance of 0.6 ohms. Now, when I say V2, I mean the voltage across the external part of the circuit or across the battery, the terminal voltage, is the total current we calculated here times R2. And that's equal to 3.3 times 4. Sorry, that's the voltage across R2. Sorry, not across the battery. Voltage across R2 is 3.3 amps times 4 ohms, which is 13.2 volts across just resistor R2. Apologies. So the external voltage is the voltage across V2 plus the parallel voltage. We only add that once because the parallel voltage is the same for both circuits. That's 13.2 plus 32, which is 45.2 volts. So that's the terminal voltage. That's the voltage which is coming out of the battery. And as usual, we expect our EMF to be slightly higher than that. Some volts are lost to external resistance. The EMF is equal to V external plus IR. Calculated the external voltage is 45.2. External current is 3.3. Internal resistance 0.6. Simple calculation, the EMF is 47.18 volts, as we expect slightly higher than the terminal voltage because of the lost volts inside the battery. Okay, so we add that to our picture. Now, I really encourage you to use PHET. I've built the circuit in PHET, and again, I do a lot more about this within my videos 4.1 and 4.2, so you can look there. The values are not exactly the same because PHET doesn't allow you to put such a fine scale on things, but they're close enough that we can measure all the different things and see that the calculations that we've used do come right. 8.3, this was very badly answered. Bulb L1 burns out after a while. So in my diagram, we're getting rid of that parallel circuit because L1 is burnt out. So we now have a simple series circuit with no branches in it. Assume the resistance of L2 remains constant. Will L2 continue to glow after L1 burns out? Choose from yes or no in support of the calculation. Now, internal resistance stays the same, EMF stays the same, but the current flowing in those two branches does not stay the same because we've now changed the circuit. The external voltage and current will not be the same. So now we must work with what we have here. And we're going to focus on the rating of L2, which stays the same because we told the resistance stays constant. So for bulb L2, P equals V squared over R. We're going to calculate that resistance. We did it right at the beginning as an example, but the resistance of L2 is 21.33 ohms. That now allows us to calculate the total resistance, internal resistance, R2 and L2. So we're going to use our EMF equation. EMF is equal to I times R plus R. So 47.18 EMF hasn't changed. We're going to be calculating the current that now flows in the new circuit after L1 is burnt out. 21.33 is the resistance of L2. 4 is the resistance of R2. 0.6 is the internal resistance of the battery. That gives us I equals 1.82 amps. Now, if you recall, we previously calculated that there would be 1.5 amps flowing through L2. So L2 will not continue flowing. Our answer is no, because it burns out, because a current higher than the rated current of 1.5 amps is going to flow through there. Now, again, with PHET, it's very easy in the circuit just to remove the bulb L1. You can see I've done it there. And you can see there the current will be 1.8 amps, which is too high for the rating of that bulb. And therefore, that particular bulb is going to burn out. So we know that. Okay, so that was question 8. It was quite a tricky one. And in this particular case, I'm going to look at the examiner's comments. And this was after marking all the scripts in the country. The examiner commented, learners always find solving electric circuits a challenge. It's important to spend more time on this section. And again, I encourage you to go back to my videos 4.1 and 4.2. Learners should always attempt to answer all the questions. The examiner recommends PHET simulations, which I've used. It's important to emphasize the moment any component burns out, the circuit changes. Only EMF and internal resistance remain the same. All other current and potential difference values must change. You saw we did that in the last calculation. Also, teachers should use various forms of the EMF equation so that learners are exposed to the different ways of calculating EMF, and emphasize that the power rating on a device is the maximum it can sustain without burning out. And you saw in that last question, because the current is too high, the power would be too high and the bulb would burn out. The main challenge candidates experienced was interpreting the circuit diagram and applying the given power and voltage ratings in the calculations. Okay, so that's one that's worth having a good look at. Right, question 9 on electrodynamics, 13 marks. Average was 53%. Now, again, looking back, you can see a fairly similar pattern over the years. And my video 6.9 is all about question 9 from page 62 in the book. If you need to know more about this section, I encourage you to go and watch that video, which is available with all the others. Looking more recently, again, November 21, the same thing, describing some sort of generator or motor. But here you see a graph coming in. 23, again, similar motor and a circuit. Oh, sorry, motor and a circuit. And 2024, interesting, no picture, no diagram of a generator or motor, just graphs. And you'll see in the November 2024, there was a lot of graphs. And that's why I really recommend that you go back and look at my video, which is all about graphs. So let's have a look at this one. The graph above shows how the induced current in a generator varies with time. Graph of induced current versus time. And name the type of generator, choose from AC or DC. Well, it's just a direct current generator because the current never goes negative. Current never changes direction. And there's a split ring commutator which inverts every second cycle. So normally that would be under the x-axis, but now it inverts it. State the energy conversion that takes place, mechanical, or you can say kinetic energy to electrical. It is a generator, so it is producing electricity from mechanical energy. Why is this generator not suitable for the transmission of electricity over long distances? Because transformers do not use direct current, and the current cannot be reduced. And it's current, high current, which causes lots of losses. Now, if this seems unfamiliar to you, on page 62 in my book, and part of video 6.9, I described the two different types of generators. A DC generator with a split ring commutator produces a graph like the one in this question 9. AC produces an alternating current, a sine wave that goes from positive to negative. So look at that if you need to know more about this. Now I'm jumping ahead to 9.7 because again, it's a descriptive question, and then we'll get back to the calculations in between. So the graph below shows how the induced current varies with time after a change was made. Fully describe the change that was made. Now, if you look at this, you can see that the period has doubled, and also the induced current has halved. So basically what's happening here is that the generator was turned more slowly, in fact, at half the speed of before. So we need to say the speed of rotation or the frequency was halved. It's not good enough just to say slower, or you can say that the period was doubled. That obviously causes a change in time, but because the induced current depends on the speed, it also causes a change in that. Now, again, in my video 6.9 and on page 62, I spent some time using this fantastic simulation. Also, there's the web address. You can look it up yourself, but it enables you to actually change the frequency, change the commutators and so on, and see how that affects the output pulse. I really encourage you to go and try this for yourself, but particularly look back at my video 6.9, and that'll really help you to understand this. Also notice in video 6.9, I do this example. It's not in the booklet. It's a previous KZN exam preparation, but again, questions around the output graph. And this will also help you prepare for this particular question. But back to November 2024, calculate the frequency at which the coil rotates in the generator. Now, obviously, the times will give you the period, but what's important to notice is that one complete cycle is not up to 0.01, but up to 0.02. Remember, that part has been inverted. So a complete wave is from 0 to 0.02. So that is the period or the time to complete one cycle. The frequency is 1 over the period, 1 over 0.02, which is 50 Hertz. Define the term root mean square current. That's a recall question you can do for yourself. But to calculate the root mean square current, let's look at the maximum current, which is 1.2. And a simple equation from your equation sheet, root mean square current is I max over root 2, which is 1.2 off the graph over root 2, which is 0.85 amps. So really not a very difficult question, and I'm sure one that you can get some marks for, so make sure you get to the end of your question paper. Right, question 10, the last of the long questions on the photoelectric effect. This was 15 marks, and this was the worst answered question in the whole paper, 34%. So please pay attention to this. My video 3 from page 17 in the book covers this area very extensively and looks at all of these 3 exam questions below, 2018, 2019, and 2020. Now you'll notice in previous exams, there were quite a few graphs. November 2019 and 2020, very different graphs. And 21, again, we had graphs, again, different. But in recent years, 23, there was attraction between 2 metal balls that had light shone on them. And 2024, we have red, blue, and green light shone onto a potassium sheet. So no graphs, just calculations and questions about it. So define the term photoelectric effect. That's a recall question I'll leave to you. But we're told that red, blue, and green light are shone simultaneously on a sheet of potassium. Each color consists of a single frequency, and 2 maximum kinetic energies are possible. There's a larger one and a smaller one. Each ejected electron has only one of these. And again, I like to add information to my drawing. Now, please notice the 2 maximum kinetic energies, because if there were 3, they could have been caused by red, blue, and green. And if anyone did not eject an electron, that would be the red light, because you should know that red light with the lowest frequency has the least energy. So which color of light is responsible for ejecting electrons that have the lower kinetic energy? That would be green. Explain the answer. Only green and blue light eject electrons. Red light does not. Green has a lower frequency than blue, and photons of blue light have more energy and eject green light ejects electrons with lower kinetic energy. Photons of blue light have more energy. So you first needed to notice that the red light would not eject any electrons, and that because this is the lower kinetic energy, it's ejected by green, which has a lower frequency than blue. The intensity of the red light is increased. What effect will this have on the rate at which electrons are ejected? Well, all you have to do is give the answer, but it remains the same. You weren't asked to explain it, but no electrons are emitted by the red light. So changing the intensity will not make any difference because the frequency of red light is lower than the threshold frequency. Now, in video 3 and on page 17 in the book, I spend a lot of time with this fantastic simulation from PHET on the photoelectric effect. You can see you can vary the intensity and you can vary the frequency. And so it really helps you to understand the different effects of frequency and intensity. So if you aren't clear on the last two questions, I encourage you to go to video 3. Then the main calculation, the electrons with the maximum kinetic energy are ejected by light that has a certain frequency. Again, let's go to our data sheet, page 38. We're going to need E equals HF. We're also going to need E equals W naught plus EK max, which is the photoelectric equation. So the energy is Planck's constant times the frequency, and it's equal to the work function plus the maximum kinetic energy of the ejected electrons. Now, we're told here, and again, I like to write it on the diagram where it's easier to see, that the frequency of green light is 5.85 times 10 to the 14 hertz. Frequency of blue light we don't know, and we're actually asked to calculate that. Now, what we're going to do is we're going to use the frequency and energy of the green light to calculate the work function, and then use the work function and the energy of the blue light to calculate its frequency. So we'll start with what we know, the green light, and move over to the unknown, the frequency of the blue light. So there's your equation. And for the green light, the work function is equal, just rearranging this equation, equals HF minus EK max. H is Planck's constant, 6.63 times 10 to the minus 34. Frequency of green light we're given, 2.65 times 10 to the minus 20 is the energy of the ejected electrons. And there we can calculate that our work function is 3.61 times 10 to the minus 19 joules. Remember, a work function is an amount of energy, which is specific to potassium in this case. Different materials have different work functions. Now, taking that across, for the blue light, we can say HF equals W naught plus EK max. And so Planck's constant times the frequency for the blue light that we're looking for equals 3.61 times 10 to the minus 19. That's the work function we've just calculated, plus the energy, 6.96 times 10 to the minus 20. And that gives the frequency of blue light as 6.5 times 10 to the 14 hertz, higher than the frequency of green light, which is what we expect because it is on that side of the spectrum and is more energetic. Okay, and then just a couple of extra questions about spectra. And in my video 3, I spent quite a lot of time looking at different types of spectrums. When a light shines, a white light, you get a continuous spectrum. When a hot gas shines and is passed through a prism, you get an emission line spectrum. And when a cold gas actually absorbs the light from a white light, you get an absorption line spectrum. Now, this is a hot gas, so we're looking at the middle one. And it says, name the type of spectrum formed, and that's an emission spectrum or a line emission spectrum. And it's because it's actually emitting those colors, where in this case, the cold gas is absorbing certain colors. Explain the presence of the colored lines in the spectrum. Well, the colored lines represent the associated frequencies or wavelengths or energy of the emitted photons when atoms move from a higher to a lower energy level. So again, those are various options of how you had to say it. So just 3 marks at the end, but worthwhile to get those marks. So don't leave out spectra. And again, I do cover these in my video number 3. So that's all for the 2024 exam paper. And as I say, the national average was hovering around 50%, but you'd obviously like to get yours higher. And these are the skills for physical science, which are in the CAPS curriculum. They're in my book on page 5. And once again, from the examiner, we have this confirmation. It's a severe lack of skills which is evident, mathematical, conceptual understanding, and integration of topics. Also free body diagrams, graphs, and equations. And that's why I really want to encourage you to focus on my Essential Skills program. But that's the end for now of the November 2024 exam paper. Thank you for watching. I hope it's been helpful.